Section 8.7 of Chapter 8 introduces the ideal gas law. This is the gas law that incorporates the relationship between all four variables that define a gas: pressure, volume, temperature, and moles of gas. The ideal gas law will allow you to calculate any single one of these gas variables if you know the other three. And just as we have been discussing with the other gas laws, it's very helpful if you know how to derive the ideal gas law and not just rely on memorizing it. So we're going to start out with the same technique we've been using in deriving the other gas laws. What are proportionalities between gas variables, any two of them? Gay-Lussac's law says that pressure and temperature are directly proportional. So we can start with that law. Boyle's law says that pressure and volume are inversely proportional. And there's no gas law that describes the variable relationship between pressure and mole amount, but we can stop and visualize what happens when you keep blowing air into a balloon that's reached its maximum volume. If you keep blowing air into a balloon that can't expand anymore and get a bigger volume, the pressure inside the balloon will become greater and greater until the balloon pops. So more moles of gas, greater pressure of gas. That's a direct relationship. So we have a proportionality that involves all four of the gas variables. And we know what to do next. Take that proportion sign and replace it with an equal sign, but we must multiply by a constant. However, in this instance, this constant is something that we are going to need to know some information about. So it gets its own special constant letter, the letter R. It is a constant. It's called the ideal gas constant or ideal gas law constant, and we will need to use that constant in calculations involving the ideal gas law. So we now have a mathematical equality involving the four variables and the ideal gas law constant. But this time we don't want to solve for that constant. All we want to do is rearrange it slightly and move volume out of the denominator by multiplying both sides of the equation by V. And if we do that, we come up with the form of the ideal gas law that you see printed in your text. Pressure times volume equals, taking the three variables R, T, N, and rearranging them slightly, pressure times volume equals N, R, T. And this is the ideal gas law. Now, before we go and do calculations with the ideal gas law, let me just remind you that chemistry builds upon itself, meaning that ideas that we've learned in previous chapters have a direct correlation or link to new concepts. So we know that N stands for moles, specifically moles of gas in the ideal gas law. Well, we learned in chapter 6 about mole conversion problems. Actually, I think it was chapter 7. We learned about mole conversion problems. So what that means is that you can use the ideal gas law, solve for N, solve for moles of gas, and then do mole conversion problems like we learned in chapter 7. You can take moles of gas and find the mass of the gas if you know molar mass of the gas as a conversion factor. You can take moles of gas and you can solve for number of molecules or number of atoms of the gas if you know Avogadro's number. So the point that I'm trying to make here is an integration idea. You want to be able to take new learning and integrate it with previous concepts. In order to do calculations with the ideal gas law, you're going to have to know the value for R, the ideal gas constant. And they're listed over here to the right. You're going to memorize at least one of the values. And if you memorize one, you should be able to calculate the other. And you may be thinking, if it's a constant, why are there multiple values? Because pressure units can vary. That's why. It's a constant, but its number will change if the pressure unit changes. So the ideal gas law constant that I memorized first has a pressure unit of atmospheres. And its value is 0.0821. Note, it's going to have all four variable units with it. 0.0821 liter atmospheres per mole Kelvin. So lots of messy units with the R value because of the four variables in the equation. Once you memorize 0.0821, all you have to do is multiply by 760 to convert atmospheres into millimeters of mercury. So R will have a value of 62.4 liter millimeter of mercury mole Kelvin. So you need to memorize at least one R value, and then you should be able to figure out what the other form of it is depending on the pressure unit required. So let's see if we can't do some ideal gas law calculations. Here's the first. Calculate the volume occupied and volume in liters occupied by 1 mole of a gas at STP conditions. And remember that STP stands for standard temperature and pressure, which has specific numerical values associated with them. In other words, experimental conditions, 0 degrees Celsius, and 1 atmosphere of pressure, or 760 millimeters of mercury. A reminder about STP conditions. So let's take a look at this data. We see that we are told that the mole amount, our N value is 1 mole. We're at STP conditions, so our temperature is 0 degrees Celsius, immediately putting that into Kelvin, 273 Kelvin. Our pressure is standard pressure, which is 1 atmosphere or 760 millimeters of mercury. And I just chose the 760 millimeters of mercury unit here, just totally arbitrary. It could be any form of standard pressure, 1 atmosphere, 760 torr, or 760 millimeters of mercury. Any of them would be fine. So we have 3 variables of the 4 in the ideal gas law. We have an N, a T, a P. We should be able to solve for volume. So we present the ideal gas law, PV equals nRT. We're trying to solve for volume, so we divide both sides of the equation by pressure, and we get volume equals nRT divided by P. And then we come to the what I call P and C stage, the plug and chug stage. You plug in the values, chug through the calculation on your calculator. It's of course very nice to have this information nicely labeled. It cuts down the likelihood of errors in plugging in numbers. Our mole amount is 1 mole. Our R value, now because I chose a pressure of 760 millimeters of mercury, I'm going to need to use the R value with millimeter of mercury units in it. So 62.4 liter millimeter of mercury mole Kelvin. That's our R value. Our temperature, standard temperature, 273 Kelvin. And we're dividing by our standard pressure of 760 millimeters of mercury. So looking at our setup and checking our dimensional analysis, our millimeter of mercury unit is canceling, our Kelvin unit is canceling, our mole unit is canceling, and we are left with a unit of liters, which is the unit we were asked to solve for volume. paying attention to these details. So getting our calculator out, I've done the calculation and have an answer, but let's just go ahead and double check it and see, do we come up with 22.4 liters? And that's what I'm showing on the calculator for the answer to this setup. So 22.4 liters is the volume occupied by 1 mole of any gas at STP conditions. And there is a name given to that volume. It is known as the molar volume of a gas at STP conditions. So we can make a conversion factor, 22.4 liters per mole at STP, or writing that conversion factor in its flipped form, 1 mole over 22.4 liters, again, valid only if temperature and pressure are STP values or conditions. Notice what this molar volume conversion factor enables you to do. It enables you to go directly from volume of gas to moles of gas if you are at STP conditions just by using this conversion factor. So, our first example was actually an exercise in solving for molar volume. Let's take a look at 2 more examples that illustrate how the ideal gas law can be combined with mole conversion problems you learned in Chapter 7. So here is our first illustration, part A, of ideal gas law mole conversion combo. Calculate the mass of fluorine gas, which occupies 985 milliliters at 58 degrees Celsius and 1.27 atmospheres. So we are clearly not at STP conditions here. Let's take this data and label it. Our volume is 985 milliliters. And notice that you see that I took that milliliter volume and converted it into liters. Why did I do that? Because I see that I've been given a volume, a temperature, and a pressure. According to the ideal gas law, if you have a V, a P, and a T, you should be able to solve for moles of gas. So I see that the volume, the temperature, and the pressure is going to enable me to solve for moles, lining me up for the mole conversion. But the R unit has volume in liters. So I know that. I'm remembering that. I don't want to carelessly plug in a milliliter volume into an ideal gas law setup. The units won't work out. So I'm going to take that milliliter unit and convert it into liters, which is what is needed to pair with the ideal gas law constant units. So converting 985 milliliters into liters, by dividing by 1,000, I come up with 0.985 liters. Taking temperature, adding 273 to that value, I get 331 Kelvin. My pressure is in atmospheres, so I'm going to need to make sure that in this particular instance, I'm using the first ideal gas law value, which has a pressure unit of atmospheres. And I'm going to solve for moles. And once I solve for moles, I should be able to use the molar mass to calculate the mass in grams. So here we go. Here is our ideal gas law equation. And perhaps you want to just stop this video, bang this calculation out yourself, and see if you agree with what I am showing here. Ideal gas law, PV equals nRT. We want to solve this equation for moles. So we are going to divide both sides of the equation by RT, giving us N equals PV divided by RT. And now we come to our plug and chug step, coming over here, looking at this equation and just plugging in the variables. Our pressure is 1.27 atmospheres. Our volume, 0.985 liters. Just reading right from the numbers that we have labeled. Now coming over to our R value in the denominator, look what I've done here. I've taken the R value and written it in its reciprocal or inverse form. That's necessary to keep from stacking units. You don't want to have units and a line and units and a line and units. Gets very messy. So we're writing that R value in its flipped or inverse form so that you don't stack units. All right, don't stack units. And then we need to divide by temperature, and I'm just going to squeeze the temperature in. Doesn't matter whether it comes right after or before the R value inverse number, as long as it's showing in the denominator. So putting in my temperature of 331 Kelvin in the denominator. Before we go any further, let's check the dimensional analysis. Our Kelvin units are canceling. Our liter units are canceling. Good thing we did that conversion. Our atmosphere units are canceling, and we are left with units of moles, which is what we're solving for. And if we do this calculation on our calculator and double check our answer, we hopefully come up with the value that I have written here. And just checking, and yep, 0.0460 moles. Now let's just stop and remind ourselves, moles of what? What gas are we talking about? And that gas is fluorine gas. Now here's where all that hard work with the first unit of this class pays off. You remember, hopefully, that fluorine is one of the diatomic elements. If you look at the periodic table, fluorine is a halogen, and halogens are diatomic elements. So when we write the formula for fluorine, we need to remember that it's a diatomic element, and that will be important for calculating the correct molar mass. So here is 0.0460 moles of fluorine. Adding up the atomic weights of 2 fluorine atoms, we get 38.0 grams per mole of fluorine, and calculating the mass of fluorine in grams, we get 1.75 grams of fluorine gas present in 0.046 moles of fluorine. So the last little technicality that I can put in here, if I were doing this problem, I would go in and label that I am trying to find the moles of fluorine gas just to keep myself on track with what I'm doing with the mole conversion problem. Our last example involving mole conversions is using the ideal gas law to solve for moles. And let's see if I can't smooth that out a little bit. To solve for moles, and then use Avogadro's number to solve for atoms or molecules. So look at this second example involving mole conversions. Calculate the number of atoms of argon gas present in 4.2 times 10 to the third liters of argon at STP conditions. So we're given a volume of 4.2 times 10 to the third liters. We're told it's STP conditions, 273 Kelvin, and just to mix it up, I chose a standard pressure in torr units, 760 torr, STP conditions. Notice what I put here on the board. You can absolutely use PV equals nRT and solve for N exactly as we did in part A. But there's a faster approach, and I wanted to illustrate it here. Because we are at STP conditions, we can use molar volume as a conversion factor, a faster approach to the answer. So here is our volume of argon gas, 4.2 times 10 to the third liters. And I am using molar volume, writing it in this form so that volume is in the denominator and my liter units will cancel. 1 mole of argon occupies a volume of 22.4 liters at STP conditions. And right away, I've converted to moles of argon, bypassing all of the work that we did here with the ideal gas law. You can use this form of the ideal gas law to solve this problem. Molar volume is just a shortcut. Remember, that number came from the ideal gas law calculation. So if we stop our problem right here, we have moles of argon, but I asked you to solve for number of atoms of argon. So here we go with Avogadro's number. It's been a while since we've used it, but it's fair to see it in any calculations throughout the rest of this semester if it applies. So 6.022 times 10 to the 23rd argon atoms per 1 mole of argon. Our moles of argon are canceling, and we are left with argon atoms. And if we take our calculator and chug through this calculation, let's hope that we get the answer that I have on the board. And I'm seeing 1.1, a reminder, our volume has only 2 sig figs, 1.1 times 10 to the 26th argon atoms. We're expecting a large number if we're talking about number of atoms, and that's what our answer is revealing.